Hello, my name is Peter Cooper from the University of Newcastle, Australia. I'm going to talk about our letter titled Ionic Liquid Adsorption and Nanotribology at the Silica-Oil Interface. 100-fold dilution in oil lubricates as effectively as the pure ionic liquid. Ionic liquids, or ILs for short, are pure salts with melting points below 100 degrees Celsius. Their remarkable physical properties and nanostructures make them potentially excellent lubricants. A problem with using ILs as lubricants is their high cost. We propose that one of the solutions to this challenge is to use ILs as dilute oil additives. In this study, we used the IL trihexyl tetradecyl phosphonium bis 2,4,4 trimethylpentylphosphonate in the oil octane. We used this IL because it is chemically stable to both air and water and is fully miscible with apolar base oils. And we used octane as a model apolar base oil because of its simple structure, well-known properties, and commercial availability in high purity. The surface we lubricated was the silica surface. To measure the adsorption isotherm of the IL onto the silica surface from octane, we used a quartz crystal microbalance, or QCM. The friction at the nanoscale was measured using atomic force microscopy, or AFM. Here we see the data for the experiment. On the left, we see the adsorption isotherm obtained by the QCM, and on the right, we see the nanofriction data from the AFM. If we look at the adsorption isotherm on the left first, we notice that the increase in surface excess with concentration is well fitted by a Langmuir isotherm. This indicates adsorption of the cations and anions of the ionic liquid onto the silica surface. At 10 mol%, the value of the adsorbed mass is close to the saturation value. This is in fact the first time anyone has measured the adsorption isotherm of an IL from an oil to a surface. Comparing the adsorption isotherm to the friction data, we notice that with the increasing adsorption of IL, the ratio of the lateral force to the normal force of the AFM tip on the surface changes dramatically. I'll now explain how this ratio, which is the friction coefficient, changes with IL concentration in further detail. This slide shows the nanoscale friction of air, octane, and the pure ionic liquid. In the case of air, the AFM tip is in direct contact with the silica surface. Friction is high and a large lateral force is observed at zero normal force, which is due to strong tip surface adhesion. When octane is introduced into the system, the tip is still in contact with the surface, but the friction and initial adhesion are slightly reduced. However, for the pure IL, the IL ions form a boundary layer between the tip and the surface, and this results in low friction and negligible adhesion. Now we will see what happens when the IL is diluted by the octane. At extremely low dilutions, in this case 0.01 and 0.05 mol%, we can see that the adhesion is eliminated. However, the similarity between the air, octane, and extremely low concentration IL friction coefficients, given by the slope of the curves, suggests that the tip is still in direct contact with the surface. For 0.1 mol% and 0.5 mol%, we notice that at low normal loads, indicated by the yellow circle on the left, the lateral force is comparable to that for the pure IL. However, when the normal force reaches 70 nanonewtons for 0.1 mol% IL, the lateral force increases rapidly and then follows the data obtained for the lower IL concentrations. Similarly, for 0.5 mol% IL, the lateral force increases between normal loads of 170 nanonewtons and 300 nanonewtons, and then follows the data obtained at lower concentrations. Push-through events in the normal force data, shown on the right, are found at the same forces, 70 nanonewtons for 0.1 mol% and 170 nanonewtons for 0.5 mol%. Together, these data indicate that while ion pairs are adsorbed to the surface at these concentrations, their density is relatively low, resulting in a relatively poorly formed boundary layer. Above the critical normal load, the boundary layer is pushed through and lateral force increases sharply. When the IL concentration is 1 mol% and above, the increase in lateral force with normal load is comparable with the pure IL over the entire range we investigated. The similarity of the lateral force data at 1 mol% with the pure IL data suggests that even at this concentration, the boundary layer is well formed and prevents contact between the tip and the substrate. To conclude, for a silica surface, a 1 mol% solution of an IL in octane is as effective a lubricant as the pure IL. This demonstrates that by using ILs as oil additives, we can achieve a similar performance to the pure IL at a fraction of the cost. Finally, the authors would like to thank the Australian Research Council and the Swedish Research Council for their support.